did was you know that the wheels for the racer have these relationships where the linear velocity is angular velocity cross r, which is the radius of the wheel, and that the torque applied by that wheel is the force across the radius. So when you put it over an FBD diagram, you have the force of the wheels essentially equaling friction, so that like in order for it to propel, the wheel will apply a force that way. We do a simple like F equals ma and the x and y components, which we tilted for this case, and you find that the force of gravity, the component in the y direction, is going to equal to the normal force, and then in the x you find that because you're idealizing it, that the acceleration, or that the velocity is constant, so there's no acceleration, you find that the force of friction is going to equal to the component of gravity in the x direction, and so you know essentially that when the force of friction at a constant velocity, that the components, you know, like two different equalities for friction, one coming from here and one coming from here, and you can set them equal. Essentially, to get the car moving in that direction and to prevent it from slipping, you have this condition here which says that the component of gravity in the y direction times mu has to be greater than the component of gravity in the x direction, which is, we came to that conclusion from the friction. And then you can say that the torque is the friction applied times the radius.
So we had to characterize our motor, and the way you do that is you like make a graph of stall torque versus RPM. And so we basically made each gear of the motor, and we did gear A, B, C, and D. And for A, we found the stall torque, and we just did that by like putting a weight and using, and then for the RPM, we just did that for A, B, C, and D. We could find the RPM. We just took the end of it and we made it like hit something, and we just used Audacity to like understand the sound of it, and that's how we found like the motor character, the speed of it. And then, but for the stall torque, we couldn't do C and D because it just wouldn't work. So we had to extrapolate our data from A and B in order to find C and D. And then with that, you could put on a graph, and then like that's how you find your motor characterization.
And we've chosen A because it provides the greatest RPM, despite the fact that it has the lowest stall torque. So this is a graph essentially of that motor characterization. So you have the 2 points. You have the stall torque, which is right here, and you have the RPM as well. So we have the two intercepts, so we can create an equation of line because we have 2 points. So you can find the slope, and then you know the y-intercept. And so we found that the equation of this line for the torque versus RPM graph looks like this. And so from there, we derived already that torque is equal to mg sine theta cross r. And we know that the velocity of the car is going to end up being omega, which is this whole equation, cross r. So now that you know all of this, you can combine it to find the velocity of the car, where the only unknowns essentially are the radius of the wheel and the angle, assuming we've already weighed the car. So from that, we created a graph, which you'll see right now,
where you can test different radii and angles, and we decided that the best angle was 0 because the line for the 0 degree had a positive slope as the radius increased, and the radius essentially we wanted to make as big as possible but be within the constraints of the tube, so it ended up being around 0.03 meters.
So this is our car, and we decided to go with a 3-wheel model because it weighed less, and we also decided to put holes at the bottom, which would also cause it to weigh less because this part of it is going to be very heavy.